In December 2024, China switched on a machine that could reshape how electricity gets made. It's called a supercritical carbon dioxide turbine, and it's the first one anywhere in the world actually connected to a real power grid. Engineers had been chasing this idea for more than 60 years, and most experts assumed it wouldn't become reality for at least another decade. But China built it, installed it inside a steel factory, and started generating power from heat that everyone else was simply letting go to waste. The numbers involved are hard to believe. Using the exact same amount of heat, this machine produces 50% more electricity than the old system, while being roughly half the size. And instead of relying on water, like virtually every power plant on the planet, it runs on carbon dioxide, the same gas your own body exhales with every breath. This isn't a minor tweak. This is a genuine challenge to the steam turbine, the technology that sat at the core of power generation for well over 140 years. Before getting into what China actually built, it helps to understand why the old method of generating electricity carries a massive, largely invisible problem. Think about where your own power comes from: coal, natural gas, nuclear, even large-scale solar setups. Regardless of the fuel source, the final step is almost always identical. The plant heats water until it becomes steam. That steam rushes through a massive bladed wheel. The wheel spins, and the spinning wheel drives a generator that produces the electricity flowing into your outlets. That's essentially how power generation has worked for over a century, with roots tracing all the way back to the 1800s. Sure, the technology has improved. Modern turbines use stronger alloys and run at higher temperatures, hot enough inside to melt most everyday metal objects. But the underlying concept hasn't changed. Heat, water, produce steam, spin a wheel. It's fundamentally the same logic used during the Industrial Revolution, just executed with far more sophisticated hardware. Here's the part that tends to surprise people. Even the very best steam turbines available today convert only around 35% of their heat into usable electricity. Out of every 100 units of heat burned, roughly 35 become useful power, while the remaining 65 simply vanish into the air or into nearby rivers as waste warmth. More than half of all the energy we burn disappears before it ever reaches a home. At a global scale, that's an enormous problem. Essentially, every power plant on Earth is largely just burning fuel and letting most of the resulting energy slip away. Something the world has quietly accepted simply because that's how it's always been done. Scientists have understood this inefficiency for a very long time and have spent decades searching for something better than steam, given that the world burns billions of tons of coal and enormous volumes of natural gas every year, essentially just to boil water. Pushing that 35% efficiency figure up to 45 or 50% would be transformative: less fuel burned, less energy wasted, lower costs, and reduced pollution all at once. The math is simple. Making it real, on the other hand, is extraordinarily difficult. Engineers eventually realized the fix wasn't a better steam turbine. It required swapping water out entirely for a completely different working fluid. The fluid they landed on was carbon dioxide, and understanding why requires getting into a strange, rarely discussed state of matter. Everything around you typically exists in one of three familiar forms: solid, liquid, or gas. Ice is solid water. The water you drink is liquid. Steam is water in gas form. But there's actually a fourth state that almost nobody talks about, one that only appears when temperature and pressure are pushed extremely high simultaneously. Push any substance past a certain threshold and something unusual happens. The liquid and gas phases stop being distinct and blend into a single, unified form. Scientists call this a supercritical fluid. Picture it this way. A liquid behaves like a strong, heavy presence, while a gas behaves like a light, fast-moving one. Very different roles serving very different purposes. In the supercritical state, it's as if those two merge into a single substance that's simultaneously heavy and fast. It sounds strange, but it's entirely real, and scientists have understood this phenomenon since the early 1800s. Here's what makes carbon dioxide especially useful for this purpose. Reaching a supercritical state with water requires a temperature of 374 degrees Celsius and roughly 220 atmospheres of pressure, an extreme environment harsh enough to tear through most metals and enormously expensive to engineer around. Carbon dioxide, by contrast, reaches its supercritical point at just 31 degrees Celsius, roughly the temperature of a warm summer day. And around 70 atmospheres of pressure, a far more manageable target compared to what water demands. Supercritical carbon dioxide is, frankly, almost surprisingly easy to produce. Once carbon dioxide crosses into that state, something remarkable happens. It becomes nearly as dense as liquid water, yet it flows through pipes and machinery with the ease of a gas. That combination of density and flow is essentially ideal for electricity generation. Density matters enormously in any turbine, since the more mass you can push through the blades every second, the more power you extract. Steam, being light and diffuse, requires a genuinely massive machine to push enough of it through to generate meaningful power, which is exactly why turbine halls at large power plants are the size of airplane hangars, with some machines large enough for a person to physically walk inside the casing. Supercritical carbon dioxide, being far denser, allows an enormous mass of working fluid to move through a dramatically smaller machine. The blades shrink, the piping shrinks, the entire power system shrinks, and because of how the underlying physics work, far less energy gets lost along the way. These systems can reach 45 to 50% efficiency, a substantial jump above the roughly 35% ceiling steam plants top. Out at that means more electricity extracted from the same heat, packaged into something far smaller with much less waste. But recognizing that something should work in theory and actually engineering it into existence are two entirely different challenges. If supercritical carbon dioxide is genuinely this much better, the obvious question is why it took until 2024 to actually build one. The honest answer is that constructing this machine is extraordinarily difficult in ways that aren't obvious from the outside. The first major obstacle is a combination of heat and chemistry. For best performance, the carbon dioxide needs to be heated to roughly 700 degrees Celsius before entering the turbine. At that temperature, most metals gradually stretch and deform under sustained pressure over time. A phenomenon engineers call creep. Imagine a metal bolt slowly lengthening year after year, simply from staying hot under constant load. In a fast-spinning turbine, even a small shift in shape can trigger a failure. Carbon dioxide makes the problem worse, since at high heat and pressure, it forces carbon atoms directly into the microstructure of certain metals, gradually weakening and embrittling them over time. A brittle turbine blade spinning tens of thousands of times per minute under enormous pressure is a serious hazard, capable of breaking apart entirely. That means engineers need exotic, specially engineered alloys designed at a microscopic level to resist both the heat and the chemical degradation carbon dioxide causes. Those alloys exist and perform reasonably well, but they cost many times more than ordinary steel. And since no one has run machines like this for 20 or 30 years under real-world conditions, nobody can be fully certain how those metals will hold up over a complete operational. The second major challenge involves the heat recuperator, arguably the hardest engineering problem of all. Much of what makes these systems so efficient comes from recycling heat out of their own exhaust and feeding it back into the incoming fluid, a step that delivers a substantial efficiency boost. But making that work requires moving an enormous quantity of heat across an extremely thin wall while both sides sit under roughly 200 atmospheres OF pressure, a level of precision that borders on absurd. The component that accomplishes this looks unlike anything else in power engineering. Engineers etch microscopic channels, some thinner than a human hair, into flat metal plates, then fuse thousands of those plates together into a single solid block containing millions of tiny internal pathways. The result is compact, extremely strong, and remarkably effective at transferring heat, but it's also nearly impossible to inspect once assembled, impossible to open for repairs, and very expensive to manufacture. If even a microscopic crack forms inside it while under 200 atmospheres of pressure, the consequences are serious. The third major challenge is speed. Because supercritical carbon dioxide is so dense, the turbine itself can be built small, but small turbines have to spin extremely fast to generate an equivalent amount of power, often tens of thousands of rotations per minute. At those speeds, conventional oil-lubricated bearings would generate so much friction heat they'd fail within hours. Engineers were forced to invent new bearing designs entirely. Some teams built magnetic bearings that suspend the spinning shaft in midair with no physical contact whatsoever, while others are experimenting with bearings that float on a thin film of the carbon dioxide gas itself. Both approaches work in laboratory settings, but both remain complex, costly, and unproven after decades of demanding industrial use. Taken together, these three challenges explain why, after more than 60 years of research, dozens of test programs, and enormous financial investment across numerous countries, nobody managed to get a working supercritical carbon dioxide system onto a real power grid until December 2024, the moment China changed the trajectory of the whole field. In December 2024, the China National Nuclear Corporation announced it had activated 2 supercritical carbon dioxide turbines at a steel plant in Jiangsu, each generating 15 megawatts of power. Together, they form a system called Chuangneng 1, the first working grid-connected supercritical carbon dioxide power unit anywhere in the world. Chuangneng 1 doesn't burn any fuel of its own. Its purpose is capturing waste heat. The steel plant was already venting into the atmosphere and converting it into electricity. Steelmaking generates enormous quantities of leftover heat that, historically, has simply been released or allowed to cool off unused. Chuangneng 1 intercepts that heat before it escapes and puts it to productive use. The results are striking. Compared to the older steam turbine it replaced, Chuangneng 1 produces 50% more electricity from the identical heat source, occupies 50% less physical space, and boosted the heat recovery efficiency by more than 85%. Over a full year, the steel plant can now generate over 70 million kilowatt-hours of electricity from heat that used to be discarded entirely, translating into roughly $4.3 million in additional annual revenue for a factory that hasn't changed a single thing about how it actually makes steel. Nothing about the underlying manufacturing process changed at all. The only difference is that a smarter machine now sits in the energy recovery loop, extracting far more value from the exact same input. The complete technical details behind Chuangneng 1 haven't been made public yet. The precise design, the specific alloys used, and the exact operating parameters aren't available for outside scrutiny. So some of the headline figures should be treated with a measure of caution until further data emerges. But the core fact is confirmed. This system is running continuously on a commercial grid attached to an active factory. That fact alone is significant. Running a machine successfully in a laboratory is one kind of test. Running it non-stop inside a working factory where it has to perform reliably day after day without being taken offline for repairs is an entirely different and far more demanding kind of proof. Chuangneng 1 has cleared that bar, and that shifts the entire conversation around this technology. The question is no longer whether these turbines can actually function. It's how quickly the rest of the world catches up, and what happens once this technology starts appearing in applications far more consequential than a waste heat recovery loop. It's worth being candid about what the Chuangneng 1 announcement actually represents, since some of the coverage has leaned more dramatic than the current reality warrants. The technology genuinely works. That part is significant. For decades, these turbines existed only in research papers, government-funded programs, and small laboratory rigs that never left the building. Going from a lab demonstration to an actual commercial installation isn't a minor step. It's a fundamentally different challenge, requiring supply chains, safety certifications, reliability standards, and real-world operating conditions no lab environment can replicate. Successfully making that leap is a genuine achievement. It means the alloys held up the heat recuperator performed as designed, the bearings survived sustained operation, and the control systems managed the extreme heat and pressure without failure. That said, where China chose to deploy Chuangneng 1 tells its own story about where this technology currently stands. It isn't attached to a nuclear reactor, and it isn't serving as the primary turbine in a large coal or gas plant. It's recovering waste heat at a steel factory, which in energy terms counts as a fairly low-risk proving ground. If the system runs into problems or needs repairs, the consequence is simply that the factory generates a bit less bonus electricity. No city loses power, no critical services interrupted. If these turbines were considered ready for absolutely everything, you'd expect to see them installed in new nuclear plants or serving as primary power sources in major facilities, where the efficiency gains would matter most and the financial upside would be largest. The fact that the first real-world deployment is a waste heat recovery application suggests the industry is being deliberately careful, building confidence incrementally and gathering the long-term operational data that bigger decisions ultimately require. That caution is the right call. Before anyone trusts this technology inside a nuclear facility, it needs to demonstrate reliable operation across 10 to 20 years. Questions around long-term carbon dioxide exposure need real. Storage for the 128mm shells was split between two locations. 24 rounds sat in racks inside the turret itself, with another 45 tucked away in the hull sponsons, the gap between the inner hull and the outer armor plating. The 75mm ammunition had its own dedicated stowage, with most of it kept in the hull beneath the rotating platform floor, near the rear wall of the fighting compartment. A further 25 rounds for that gun were held in the turret, positioned to the right of the weapon itself. The 1,000 rounds carried for the machine gun were stored in armored ammunition boxes. To aim both main guns, the gunner used a TWZF-1 periscopic sight offering 10x magnification, far sharper than anything fitted to an Allied tank at the time, capable of precise shots out past 2.5 miles, or roughly 4,023 meters. Two separate scales on the sight's right side tracked elevation for the 128mm and 75mm guns independently. The eyepiece itself never moved. Instead, an internal mirror linked directly to the gun mount tilted along with the barrels, keeping the gunner's eye in a fixed spot for quicker target acquisition and inside 0.75 miles, or about 1,207 meters, the shell traveled fast enough that the gunner could point almost straight at the target, past 1.24 miles, or roughly 2,000 meters, though he had to compensate for the shell's arcing drop. Getting that first shot right depended on knowing the exact range, and a new vertical rangefinder from Zeiss was supposed to solve exactly that problem. The turret was built with mounting brackets already in place on its roof, ready to receive the device, but the rangefinder itself never actually arrived. Without it, the gunner had no choice but to estimate distance using the markings in his sight. Had it been delivered, the rangefinder would have sped up and sharpened aiming, offsetting some of the delay caused by the gun's slow reload. Instead, engagements took longer to set up, and accuracy dropped off noticeably at long distances. German planners saw the Maus as a breakthrough weapon capable of smashing through even the strongest fortified lines, and the intent wasn't just a strong front plate, but roughly equal protection all the way around. The glacis plate measured 7.87 inches, or 200 millimeters, thick, with the side armor coming in at 7.09 inches, or 180 millimeters. The roof carried 4.06 inches, or 103 millimeters, of steel to guard against plunging artillery fire. Up front, the belly plate was 4.09 inches, or 104 millimeters, thick enough to survive a direct hit from a Soviet TM-4 for anti-tank mine.